Hello guys, welcome once more to our YouTube channel. It's always a pleasure to have you here. Thank you so much for those of you who are huge admirers and sticklers for our work. We appreciate you, we love you, you're the reason why we keep going. And yeah, leave your thoughts down in the comment section down below after going through this episode. I loved it myself, so I hope you would love it too. Let's go. Which of the following statement concerning semiconductors is correct? Okay, so we're just going to go through every one of the statements and then see which one is correct. So it says pure semiconductors at low temperatures are good conductors for electricity. Wrong. Okay. Well, semiconductor materials are examples of materials with a negative temperature coefficient of resistance. What does that mean? That means that as temperature increases, their resistance to the flow of electricity reduces. Okay, so it means that their conductivity increases with temperature. All right. Metals, on the other hand, have a positive temperature of positive temperature coefficient of resistance. Okay, so as temperature is increasing, the resistance to the flow of electric current in a conductor increases. Why? Because, well, the atomic vibrations also increases, thus reducing the mean free path of electrons. Okay. B says current in a p type, so A is off. Okay, semiconductor at low temperature are good conductors. No, instead of high temperatures, they'll be good conductors of electricity. B says current in a p type semiconductor involves the motion of positive atomic ions. That's not true, right? Semiconductors, in fact, current is always a function of what? For extrinsic semiconductors, you would rather have the motion of the majority charge carriers. So for a p-type semiconductor material, you would have the motion of what? The holes, all right? Because the p there stands for positive charges, which are the holes. And then for the n-type, which the n stands for negative, you would have the electrons. So B is off. C says an n-type semiconductor contains a lattice of positive ions. Correct. Why? Because the n-type semiconductor material has majority charge carriers to be what? Electrons, the n as a negative. So when they give off those majority charge carriers to the sea of delocalized electron cloud, what happens to the atomic structure, to the lattice structure of the extrinsic semiconductor material? Well, the ions are left positive. All right, so C is the right answer. Good. So our answer here is C. A charged particle is moving in a uniform magnetic field. Okay, let's show you what is happening. This our charged particle gets into the uniform magnetic field, and then the moment it gets into the uniform magnetic field, you realize its motion, right? Circular. Why? Because the direction of motion of this charged particle is perpendicular to the direction of the magnetic field. And so you notice that there's this force. There is the arrow, this force right here. Okay, let it come again. Look at this force pointing towards the center. Can you see that? From the circular part down towards the center, that's the centripetal force right there. And so the centripetal force provided by what? By this force, dq of v sine theta. Okay, because it's entering perpendicular, the direction of motion of this charge is perpendicular to the direction of the field. Theta here is 0. It's 90. So you have sine 90, which gives me 1. So I basically have this force. This centripetal force that's pointing it towards the center like that, causing it to move in the circular path to be bq of v. Okay, so that's what we know. All right, now its momentum changes, but kinetic energy remains the same. Kinetic energy remains the same. That's true, because you're moving with uniform circular motion. All right, this is a uniform circular motion, and so the speed of the particle in the circular part is the same. But is the velocity the same? No. Why? Because you're constantly changing direction. Look at this. You're constantly changing direction in the circular path. So because you're constantly changing direction, the velocity of that particle is constantly changing directions too. And so the momentum cannot stay the same. So momentum change is correct, okay? Because it's a constantly changing direction. Since momentum is mass times velocity, and the velocity is constantly changing, it means that the momentum is constantly changing too, even though the speed is constant, making the kinetic energy to be constant. So A is the right answer. But let's see why the others are wrong. Both momentum and kinetic energy remain the same. Not true. Why is momentum not the same? Because velocity is changing, all right? Both momentum and Ke change. Ke does not change. Why? Because the particle travels with uniform speed in the circular path. The Ke changes, but momentum remains the same. Momentum does not remain the same, right? So that's off. So our answer here is A. Okay, guys, we always advise that to get the best out of our YouTube channel, you always pause the video, try to solve the problem yourself, and then come up with your own solution. Where you have difficulties, you then follow up with what we have done so that you are able to smoothen out your difficulties. Okay, so we have that. All right. Uh, EMF here, you just pause the video and read the question. All right. So EMF is proportional to change in temperature. Okay. So that is for a linear thermocouple, by the way. And the question, the original question has for a linear or assuming that the thermocouple maintains linearity with temperature difference relative to the induced EMF across its ends. So there's that part of the question. Just too bad we did not type all of it out. So bad. So yeah. So EMF has to be proportional to the change in temperature, which that means that, well, EMF is equals to a particular constant times change in temperature, and so that constant is E over change in temperature, right? So let's plug in the values for this Roman one, the EMF across the ends of these objects, the hot and cold object. It's basically 5 millivolts. Okay, so if we get that ratio, we're actually going to get K to be 5 times 10 to the negative 5 volt per degree Celsius. Now, delta theta for this part 2, right? Because we're looking for theta. Okay, so it's this temperature difference between the cold and hot object that creates this change in EMF across their ends. And so we're going to calculate that change in temperature, delta theta, to be, again, our EMF here is negative 1.5 millivolts, right? Divided by our K. Our K is this constant that we got here. Plug that in. So our delta theta is negative 30 when you punch this. Now, but remember that delta theta is what? Change in this temperature, theta minus 50 degrees Celsius. So that has to be equals to negative 30. So you realize that our theta is 20 degrees Celsius. And so our answer is A. Okay, this question is really about which statement is implied by the first law of thermodynamics. Really, guys, really, I think everyone should know by now that the first law of thermodynamics is basically a statement of the law of conservation of energy. And so D is basically the answer without going through. But I've taken our time to explain why A, B, and C are wrong. So first law of thermodynamics mathematically is dq equals to U plus dW. Okay, that's if work is actually done by the system and then heat is supplied to the system. So our dq is 0 only for adiabatic processes. Okay, that's a process where, of course, no heat enters or leaves the system. So dq is 0, and so you realize that, well, work can be done at the expense of the internal energy of the system. Okay, rendering A and B to only be true for adiabatic processes, because A says no heat enter or leaves the system. That's only for adiabatic processes. Change internal energy equals external work done. That's only for adiabatic processes again. The temperature remains constant. Well, that's only for isothermal processes. So the general concept of the first law of thermodynamics is basically a statement of energy conservation, and so every other statement that is mentioned here is basically a subcondition, all right, or a subset of all the possible scenarios you can have within the first law of thermodynamics. Okay, good. And so our answer here is D. A fixed mass of ideal gas undergoes changes of pressure and volume V as shown in the graph in figure 7. Which of the following gives the coldest and hottest points? Okay, so this is our graph. Okay, so but I just want you to realize that the ideal gas equation says PV equals nRT. Notice that PV is proportional to T. Okay, so N is a constant, basically the number of moles of the gas in that container. R is a universal gas constant. So PV here is proportional to the temperature. So what does this mean? It means that the point with the highest temperature is the point with the biggest PV product, and vice versa. Okay, Y has the biggest PV product. So I just get to come here to this graph. My P here is 1. My V here is 1 for Z. So product 1 times 1 gives me 1. So my PV product here is basically just 1. For X, I have 4 times 1, which gives me 4. For Y, I have 5 times 1, which gives me 5. So because PV product for Y is biggest, Y has the highest temperature, okay? And then X followed by X, and then Z is the last. So Z has the least temperature. Z is the coldest point of all 3 points. I hope that makes a lot of sense to you. Okay, so our answer there is D, all right? A potential difference of 600 volts is applied across the plate of a power plate capacitor. The separation between the plates is 3 millimeter. A magnetic field exists between the plates. The electron is projected parallel to the plate as shown. in figure 8, with the speed of that moves undeflected between the plates, the magnitude of the direction of the magnetic field is. All right, so first thing first, if you have a charged particle moving through a B field and an E field, you can basically calculate the strength of the magnetic field by getting the ratio of the E field to the speed of the particle, okay? So you realize that, well, our E field is going to be, we can calculate the strength of the E field here, get the potential difference between the plates, so it's 600 volts, all right, divided by the separation of the plates, which is 3 millimeters. So we get that ratio, we get the strength of the E field first. So that strength is 2 times 10 to the power 5 volt per meter. Now we can substitute this strength of the E field back in this equation to get the strength of the B field. So E is 2 times 10 to the power 5. What is the speed of the particle? The speed of the particle is 2 times 10 to the power 6. So you plug that in there, and so you realize that your B field strength is 0.1 Tesla, right? And so our answer is B. Now, why is the answer B, right? You are going to use Fleming's left-hand rule, okay? Because this is the motion of the electron, and you want to deduce, you know, the direction of the B field. You want to deduce you know the direction of motion of the electron, and then you want to deduce the direction of the B field. Okay, so you use your Fleming's left-hand rule, your thumb, of course, you orientate your thumb and your first finger and your second finger such that they are mutually perpendicular to one another. The thumb points in the direction of motion of the charged particle, which in this case is your electron. The first finger points in the direction of the field, which is what you want to deduce, and then your second finger points in the direction of the current. Okay, so current flows in the opposite direction to the charge, right? Yeah, and so you basically do that, and then you deduce. Too bad I cannot deduce it. Like, this is supposed to be a video where you can see me, but unfortunately, we'll just get that done some other time. Yeah. But I had time to do it at the center with our students so they could really understand why it is out of the paper. But again, if you don't know why it's out of the paper, you can get my number and then shoot me a message on WhatsApp. All right, let's talk about it. Okay, yeah, we can talk about it on WhatsApp. All right, so size B. 20. Three wires X, Y, and Z carry currents of equal magnitude. The direction of the currents are as shown. The direction of the resulting force experienced by Y due to the currents in X and Z is. Okay, that's easy. Now, the first thing you have to notice here is that for two long parallel current carrying conductors, if the current flowing in them, if the direction of current flowing in them is similar, so it means that look at this guy X and Y, they have similar direction of flow of current. So this means that the resulting force between them is going to be attractive. Okay, we say in magnetism and in uh, um, electric fields, or when you're studying charges, electrostatics, that like charges would repel and unlike charges would attract. Then we say magnetism, that like poles will repel. So if I get an north pole close to the north pole, they'll repel. But in this aspect of magnetism, where you're talking about current carrying conductors, if the currents are in the same direction, then they rather tend to attract. So like currents rather attract, and then unlike currents rather repel. So Y and Z here would be repelling each other. Okay, that's the very first thing you have to know. This came in 2015 GCE. So let's indicate the directions here. And so for this Y, first and foremost, since we know that X and Y are carrying current in the same direction, so X is going to be attracting Y. So this is the force X exerts on Y. So X exerts a force on Y in this direction. It's attracting it. Y in turn exerts an opposite but an equal but opposite reaction force on X. Okay, and so this is the force here. Force X exerts on Y. Okay, I've messed this up a little bit. Oh, Y exerts on X. Yes, correct. The force Y exerts on X. This is it, acting on X. So if you get over here, these two guys will be repelling each other, right? So the first thing is that Y is repelling Z away. So the force that Y exerts on Z is this force repelling it away. And then Z exerts a particular force on Y, which is repelling it away too. So this is the force right here. Z is pushing Y away. So you realize that the two forces that are acting on Y are to the left. And so the resultant of these two forces are basically just going to be to the left. right? So the answer there is very easy. The answer is B. Okay, you have thorium decays to lead-2O6 by a series of 4 radioactive decays. Each decay involves one emission of either a single alpha particle or a single beta negative particle. The value of X is, okay guys, you have to take note of this. This is either, okay? So it's possible that you eject all 4 of the particles are only beta negative particles, or all 4 of the particles are only alpha particles. So we don't know that. So we have to write an equation, a decay equation, that permits us to correctly interpret this word either. Okay. So the first thing we're going to do, oh Jesus, I just displayed everything I want. All right, that's fine. Let's look at it. So atomium decays to lead-2O6, and then U number of alpha particles plus V number of beta particles. All right, but remember that there are 4 of these decays, and so what happens is U plus V has to give you 4. All right, so that's our equation 1 right there. We don't know how many alpha particles, we don't know how many beta particles, but we know that it's either an alpha or a beta particle, and there are 4 of these decays. So it means that there are 4 of either this or this. So either U plus V has to be equal to 4, and that is interpreted as what? U plus V equals 4. And so you have X to be equals to 206 plus 4U, this is charge, this is mass conservation, plus V times 0, which is just 0. So you have equation 2 there. From charge conservation, 81 will be equals to 82 plus 2U minus V. That is from charge conservation equation 3. So using 1 and 3, so this is our equation 1, this is our equation 3. Why are we using 1 and 3? Because, well, 1 has just U and V, 3 has just U and V as unknowns. So we can use 1 and 3 to solve for U and V simultaneously, and then put in equation 2 and then get the value of X. So we can get U. We don't need V. Why? Because we are looking for X, and then the only thing that is stopping us from getting X is just U. So just get U and then put it in the equation 2 and then get X. So we get U here, this one. Put U in equation 2, you have X to be 210, and so our answer is C. For naturally occurring nuclides, the variation with nuclear number of the binding energy per nucleon is as shown in figure 10. Which of the following is the total binding energy of the nuclide? 154.64. Good. All right, so total binding energy, guys. So this is our binding energy per nuclide. So you realize that, all right, this is our goal. This is a nuclear number 156. So what's the binding energy per nucleus? 1.3 picojoules. So get 1.3 picojoules multiplied with 156, which is the total nuclear number. That gives you what? The total binding energy. And so we're basically going to do that. 156 times 1.3 picojoules, and so that gives us 203 picojoules, and our answer is B. A tensile force F1 causes a wire to stretch to a length x1. When the tensile force is increased to F2, the length of the wire is x2. The wire obeys Hooke's law. What is the additional energy stored in the wire as the length increases from x1 to x2? Okay, so from Hooke's law, we have that F1 equals to kx1 minus L0. Why are we using x1 here? Because that's the stretch length. Okay, so if you get that stretch length minus the original length of the wire, you get the extension. And so K times the extension gives you the force, and that's basically Hooke's law. So that's equation 1. Equation 2, of course, now F2, we have increased the force to F2. So the stretch length has now increased to X2. So it means that the new extension will be X2 minus L0, which is the original length, right? Multiplied by K. So that gives you the force. Again, Hooke's law. Now, the energy is half kx squared. You want to calculate the extra energy as a result of increasing the force from F1 to F2. So what you're going to do is you're going to find the extension when the force increases from F1 to F2. And what's that extension? Well, the final stretch length minus the original stretch length. So x2 minus x1, all right? So that gives you the extension that you gain when you increase the force from F1 to F2. This is the new extension that you get. And so you have half kx squared. All right, that's the energy stored in that stretch material. So this is our equation 1, this is our equation 2. We can divide all through by k. All right, so you notice that I've divided equation 1 by k and then divided equation 2 by k, and then I basically subtract 2 from 1. Okay, So we are going to get f1 over k minus f2 over k to be equals to x1 minus x2, because this negative L0 goes to this positive L0 down here. Okay, so we now have this. We can go over and say, all right, our k then would be f1 minus f2 over x1 minus x2. Okay, because you're basically coming here and making k the subject. All right, so putting in 3, can come back here and put k in the energy. Remember that what we're really looking for is the energy. Okay, and notice that the energy here is not expressed in terms of k. That's why we're changing equation 1 and 2 to eliminate L0 and k. All right, so we can come back here and get this k, put in equation 3, which is the energy now. So put that k in equation 3, you have this, you simplify that, you have the energy to be this, and our answer is A. An experiment is carried out to determine the Young's modulus E of steel using a vertical wire of length L and cross-sectional area A. Various weights W are suspended from the wire. A graph of extension E against weight W is plotted as shown. The green of the graph represents. Okay, so we have E to be FL0 over EE, right? So our extension there will be L0 over EE times F. So if I'm plotting extension against F, which is basically the weight, you basically notice that, well, our slope will be L0 over EE, but L0 there is just capital L. So notice that our answer there is clearly this D. So D is our answer now. Yeah, D. Sorry about this, guys. It's actually D, right? Yeah, it's D. It's D. Okay, sorry about this wrong animation. So it's D there. The given graph in figure 12 shows how the attractive force F between two atoms varies with their separation D. It may be assumed that the atoms are originally at their equilibrium spacing, which area represents the energy required to separate the atoms to infinity. Okay, guys, slow down. So if I'm assuming that they're originally at the equilibrium separation, so the atoms are right here, right? So if I'm going to get the atoms all the way to infinity, that's me stretching them apart, all right? The distance that the intermolecular distance or the interatomic distance is increasing all the way to infinity, where I get the net force between the atoms now to be 0. Okay, so you realize that, all right, I'm going to now find the area under this force separation graph from this point all the way to infinity, because this is where the atoms are completely free, or they exist at infinity. Okay, so you notice I'm just going to be getting A2 plus A3. All right, so our answer there is A. The speeds of three particles are 2u, 10u, and 11u. Which statement about their speed is correct? Okay, we're just going to go through the mean speed here, which is c bar is equal to, you just get all the speeds, you sum them, and they divide by the total number of speed molecules that you have there. That's the average speed now. That's what you call the mean speed. And so the average speed there is 23u over 3. Now, the next thing we can get is the mean square speed, which is what you call mean square speed. All right, the mean square speed. Now, notice that in physics, the mean square speed is what is useful. The square mean speed is what is not useful. So getting this average and then squaring it has no sense, makes no sense in physics. Okay, so you never use that in physics. So to come and say 2u plus 10u plus 11u divided by 3, all that squared, that has no sense in physics in terms of looking for the mean square speed. No, the square mean speed, sorry. So the mean square speed is what has value in physics. So you're getting the speeds and then you're squaring each one of them first. Then you divide now by the total number of atoms or molecules right there. There are 3 of them. So you get the mean square speed as 75u squared. Okay. Now, the root mean square speed, of course, you write it as this. It's basically square root of this mean square speed, all right, which gives us 503u. Now, if I get the root mean square speed minus the mean speed, that gives me approximately 1u. I think it's going to do you a lot of good to try to punch this out on your calculators. So you realize that that gives you approximately 1u, right? And so our answer is A there. All right, guys, thank you so much for watching the video. If you enjoyed it, leave comments down in the comment section below, and please subscribe, like the video, share to your friends and to other people to view our channel. Thank you guys so much for those of you who love our work, who stick around, who leave us comments. Thank you so much. We appreciate you. We appreciate the love. You are amazing. We love you. Thank you. You're the reason we do this. You're the reason we keep going. Thank you so much. Stay curious all the time. See you next time.